Welcome to lecture 29. This is week 6 and we are talking about direct search methods for unconstrained multivariable optimization problems. In our previous lectures, we have introduced simplex method, which was a very popular direct search method. In today's lecture, we will introduce one more direct search method known as Hooke-Jeeves pattern search method. So, we will first introduce what are pattern directions, what do you understand by pattern search, and then we will give the algorithm an example for Hooke and Jeeves pattern search methods. Let us start with some discussion on univariate search. The univariate search refers to minimizing a multivariable function with respect to one variable at a time, keeping all other variables constant. So, this means if you have a multivariable function, you pick up any one variable, keep all other constant. So, maximize or minimize the function with respect to only one decision variable, keeping all other constant. For doing this, you can use any direct search techniques that you have learned for single variable optimization. So, the basic equation that describes this univariate search is this, which tells you that you update the decision variable at k plus 1 iteration as the value of the decision variable at kth iteration plus some increment. In the equation, the increment is shown by alpha. K indicates iteration number. Now, how do you calculate the increment alpha? So, that can be calculated by solving a minimization problem, where you are minimizing f of x I at kth iteration plus alpha, and your decision variable for this minimization problem is alpha. In other words, you calculate alpha to minimize the function in the coordinate direction x I. So, you find out alpha here, so that you minimize f of x I at kth iteration plus alpha. If the problem, as we have just expressed by these two equations, fails to improve function value, that means for a minimization problem the function value is not decreased, then instead of taking a positive increment, we take an increment of minus alpha. So, basically what we do then is we take x I at k plus 1 is x I k minus alpha I. Similarly, this will also changed, and you have to incorporate minus sign, or you have to replace the positive sign by the minus sign. Now, if that also fails, that means when the problem as expressed in the equation shown fails to improve function value, you first take an increment of minus alpha. If that also fails, the decision variable x I is left unchanged, and we continue search with the next decision variable. The univariate search may not converge always. However, univariate search is effective, that means it converges quickly for a quadratic function of the form x transpose C x, or you can write it as sigma I equal to 1 to n C I x I square. So, if your objective function is quadratic, of the form shown, the univariate search will generally converge quickly. This is because here the search directions line up with the principal axis. So, what does it mean? It means that for the quadratic function sigma I equal to 1 to n C I x I square or x transpose C x, if you look at the contours will be like this. So, for a two variable function, let us say I have this is x 1, this is x 2. So, you start let us say at x 0, you perform univariate search and let us say this is the minimum. So, you go in this direction x 1 keeping x 2 fixed, then keeping x 1 fixed, you go in the direction of x 2 and you can hit the minimum. So, the search becomes efficient because the search directions, that means this direction and this directions, line up with the principal axis. However, this method does not work so well for more general quadratic functions as shown by this equation, which is sigma I equal to 1 to n, sigma j equal to 1 to n d I j x I x j. Here if you plot the contours, it will be like this, and you can see if you start from here, so it is my x 0, you go in this direction, then you go in this direction, then you go in this direction, then you go in this direction. This is how you will travel. So, it takes more time to converge for the quadratic functions which are of not x transpose C x type. Now, let us try to understand the basics of Hooke and Jeeves pattern search methods. So, let us try to understand first what we mean by pattern directions. In the univariate method that we have just seen, we search for the minimum along the directions parallel to the coordinate axis. So, for two variable problem, maybe we will first keep x 2 fixed and move in the direction of x 1, which is parallel to the coordinate axis. Again you move in the direction of x 2 parallel to the coordinate axis. This makes the convergence process slow. Sometimes the method may not even converge. These problems can be avoided by changing the directions of search in a favorable manner instead of retaining them always parallel to the coordinate axis. So, instead of taking the search directions parallel to the coordinate axis, we can take the directions which are favorable to us, means we can take the search directions toward the optimum point. These directions are known as pattern directions. The process of going from one point to another is called a move. For minimization of a function, a move is a success if the function value decreases after the move, otherwise it is a failure. Similarly, for maximization problem, a move is a success if the function value increases after the move, otherwise it is a failure. So, a successful move will improve the value of the objective function, otherwise the move will be considered as failure. Let us look at the figure. The univariate search will go as 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, so on and so forth. but the pattern direction will go as 1 to 3, because if you look at the directions 1 to 2 and 2 to 3, and if you now join 1.1 and 3, you see that this direction basically is pointing toward the optimum. So, this is the pattern direction. Similarly, instead of going from 3 to 4 and 4 to 5, if I go 3 to 5, this direction is again pointing to the direction of optimum. It is a pattern direction. So, the figure quickly tells you that if I orient my search in the direction of pattern direction, I will be able to converge much more quickly than it is possible by univariate search. If the objective function is quadratic in two variables, pattern directions pass through the minimum. Although for general multivariable functions this property is not retained, we still can use this idea to achieve rapid convergence. For a two variable function, at least two linearly independent search directions are required to go from one point to another. What you see in the figure is a two variable function, contour of two variable function. So, from going from one point to another, you need at least two linearly independent search directions. For a n variable function, we need n linearly independent search directions to go from one point to another point. There are many possible combinations of such directions. Some combinations will converge quickly compared to other combinations. Now, the methods that use pattern search directions as such directions are known as pattern search methods. So, pattern search methods are defined as those techniques which use pattern directions as their search directions. There are two well known pattern search methods, and we will consider both. The first one is Hooke-Gibbs pattern search method, the another one is Powell's method. It is also known as Powell's conjugate direction method. In general, a pattern search method takes n univariate steps, where n denotes the number of design variables or decision variables in the objective functions, and then searches for the minimum along the pattern direction S I. We can define S I as x I minus x I minus n, where x I is the point obtained at the end of n univariate steps. X I minus n is the starting point before taking n univariate steps. So, basically the pattern directions is the difference between x I and x I minus n, where x I is the point obtained at the end of n univariate steps and x I minus n is the starting point before taking n univariate steps. So, now let us start talking about Hooke-Gibbs pattern search methods. The pattern search method of Hooke and Gibbs is a sequential technique. Each step of this method consists of two kinds of moves: the exploratory move and the pattern move. So, there are two important steps involved at each iteration of Hooke and Gibbs method. The first is the exploratory move and the second is the pattern move. The exploratory move is performed systematically in the vicinity of the current point using one variable at a time technique, that means univariate search technique, to explore the local behavior of the objective function. The goal is to obtain the best point about the current point. So, in the first step of the Hook and Jeeves pattern search method, which is known as exploratory move, we search systematically the vicinity of the current point, and we do this by applying univariate search technique, that means one variable at a time search technique. So, we explore the local behavior of the objective function so that we can obtain the best point around the current point. So, if the function value is improved after this exploratory move, we will call this move as success, otherwise it is failure. If the exploratory move is successful, the next will be a pattern move. The pattern move is then performed using two best points, the current best point and the best point in the previous iterations, to take advantage of the pattern direction. We have just seen that if we search along the pattern direction, there is a much higher probability that we will converge to the optimum point more quickly. So, first we perform exploratory move to obtain the best point about the current point, and then using the current best point and the previous best point, we determine the pattern direction and we perform a pattern move. Again, if the pattern move leads to improvement in the objective function, we will accept the pattern move, otherwise we will discard it. We will see more when we discuss the algorithm. So, the exploratory move is performed by one variable at a time technique. Given a specified step size, the current point, that is base point we call, is perturbed in positive and negative directions along each variable and the base point is recorded. So, for a multivariable function, the exploratory move is performed by one variable at a time technique. We have to first specify a step size, that means the amount by which you are going to perturb each variable at a time in the positive direction as well as in the negative direction. We call the current point as base point, and this current point or base point is perturbed both in positive and negative directions along each variable, and the best point is recorded. The current point is changed to the base point at the end of each variable perturbation. The exploratory move is a success if after all the perturbations we get a point different from the original point. Otherwise, the exploratory move is a failure. Note that when we perform exploratory move, we retain the best point. So, at the end of exploratory move, if the point we get is different from the original point, that means we have improved on the function value and the exploratory move will be success. Otherwise, the exploratory move is a failure. Note that the outcome of the exploratory move is always the best point, and the best point is now considered as the new base point. So, now The pattern move is performed along pattern direction by considering the current best point. So, x at kth iteration and the previous best point, that is x at k minus 1 iteration. The pattern direction is obtained by connecting these 2 points as x p at k plus 1 iteration is x at kth iteration plus the difference of x at kth iteration minus x at k minus 1th iteration. So, this is the equation which you have to use to perform pattern move. So, basically the pattern direction is obtained by connecting the 2 best points, current best point and the previous best point. Then you can perform the pattern move using the equation shown. If the pattern move does not improve the solution, the move is not accepted and the exploratory move is performed with reduced step size. So, if the pattern move does not improve the function value, we will not accept the move, we will reject the move and then we perform exploratory move again, but then exploratory move is performed with reduced step size. You can say divide the step size by 2 and can perform the exploratory move again. The search is terminated when the step size becomes sufficiently small. Step size will go on decreasing because whenever the pattern move does not lead to the improvement of the objective function, we will perform the exploratory move with reduced step size. So, the stopping criterion is that the search method is terminated when the step size becomes sufficiently small. So, this sufficiently small value we must specify, maybe 10 to the power minus 4. So, now let us present the algorithm. The step 1, we assume the current solution, call it as base point, let us call it as x c. We have to define increment in each direction. That means, if you have 2 variables, we will define step size for increment for both of these 2 variables. If you have n variables, we will define n increments. They may be all same or different. Set the iteration counter I equal to 1 and x equal to the current solution or base point x c. Now, step 2. So, we calculate the function value at the current base point and then perturb in the positive direction function value when after perturbing x in the positive direction and the function value after perturbing x in the negative direction. So, we have 3 function values, you find the minimum and then take the x which corresponds to minimum value of the function. For example, if this is the case for the minimum value of the function, we take x as x I plus delta I. Now, in the step 3, we check if I is equal to n or not. If I equal to n, that means that you have perturbed all the variables. So, if I is not equal to n, set I equal to I plus 1 and go to step 2 where we perturb in the other directions and find out the minimum and set x corresponding to f minimum. Otherwise, that means if I equal to n, we have perturbed all the variables, we check x, the current x that is obtained is different from the original x or not. If x is not equal to xc, the exploratory move is success, otherwise it is failure. So, this is the algorithm for the exploratory search. Now, the overall algorithm will be as follows. So, in the step 1, you do initialization, where you define the starting point, given the starting point x 0, define all the increments in all directions. Step reduction factor alpha, we consider a value greater than 1, so that we can decrease the step size. Termination factor epsilon, a positive value, small positive value, and set the iteration counter k equal to 0. Now, in the step 2, you perform exploratory search with x k as base point, k equal to 0. So, x of 0 is the base point. So, perform exploratory search with the current solution as base point. Let x be the result of the exploratory search. If exploratory search is a success, we consider the value of x at k plus 1 iteration is the current value of the x, and go to step 4, where you perform the pattern move. After performing the pattern move, we perform exploratory search, and for that you take the base point that you obtain after performing the pattern move. Let us say the output is x k plus 1. So, if the function value at this x k plus 1 is less than the function value at x k, we go to step 4, where we perform a pattern move again. After that, we perform again exploratory search, and this continues. If the exploratory search was not a success, if the exploratory search was not success, then we go to step 3, where we first check if the increment is sufficiently small or not. If the increment is already sufficiently small, we will stop, and the current x solution is the approximate value for the solution of the problem. If the step sizes are not sufficiently small, we perform the exploratory move with reduced step size. So, for that what we do is we set the step sizes as the step size divided by the step reduction factor alpha. Note that alpha is greater than 1. So, the step size is going to reduce, the increment is going to reduce, and then go to step 2, where you perform the exploratory search again with this reduced step size. So, this is how the overall algorithm works for Hooke-Gibbs pattern search method. So, now let us take an example. We have considered a function of 2 variable, which is 8 x 1 square plus 4 x 1 x 2 plus 5 x 2 square. The starting point is minus 4, 4, and we want to find out the minimum of this point, minimum of this function by Hooke-Gibbs pattern search method. So, to start with, I have to define the step size. So, let us consider the step size as one. I have to consider the step reduction factor alpha, let us consider this as 2. I also have to consider the termination parameter epsilon, let us say 10 to the power minus 4. So, these are the values we will initially assign. Now, you will start exploration move about x 0, which is -4 as given. The value of the function at this given starting point is, if you calculate, you will get 272. Now, we will perform univariate search. So, let us keep x 2 fixed, change x 1 as -4 plus 1. Look at here, -4, you get 1, which is -3. So, the new point that you get is -3 for x 1, -4, x 2 is fixed. So, the function value at -3 -4, if you calculate, you will get as 200, which is less than the previous value 272. So, the move is a success. So, then we will fix x 1. So, let me again start on a fresh page. So, we keep x 1 fixed at -3 and now perturb x 2. So, I will perturb x 2 as same way. So, -4 plus 1 will be equal to -3. So, let us find out the function value at -3, which you get as 153. If you remember the previous function value, that was 200. So, again the move is success. So, after one iteration, from x 0 I go to x 1, where this point I get as -3 -3. And the value of the function is 153. So, let us remember this. So, I will again start with a new screen. So, now exploration was successful. So, we have to do the pattern move. So, pattern move will be done as x 1 plus 0. This you can write as, if you remember, this is -3 -3. So, this is -3 -3 and the initial was given as -4 -4. So, this if you compute, it is -2 -2. So, the function value at this you calculate now and it is 68. So, the pattern move has improved the function. So, now what we will do is we will perform exploration around this point, which is x p 2. So, if you do this, you will see that the positive increment on x 1 and positive increment on x 2 will produce a success, and the result will be x 2, it will be -1 and -1. and f at this point the value will be 17. See, the function value has improved. So, we will do again pattern move. So, we will take this new base point -1 and we will do the pattern move, and we will continue this till the search direction, the increments are small, here less than epsilon value equal to 10 to the power -4. The final solution is 0 0, and you will see that as we approach the function value 0 0, these step sizes will be very small and will terminate. With this, we will stop the Hook-Jeeves pattern search method.